Okay, C point is response of equilibria to the temperature. Means what happen if we change the temperature of the equilibrium conditions. So for that, there are two reactions to be considered, exothermic reaction and endothermic reaction. So suppose here we consider exothermic reaction. That means there is a, suppose A converts into B plus there is a plus delta H is present, means heat is produced, heat is liberated because of reaction is exothermic. Reaction is exothermic. So in exothermic condition, this side has higher energy. Energy is rises at the product side. When energy is rises, so that time K is increases with the higher temperature. When temperature is increases, K is increases. So in exothermic reactions, this heat is evolved out. The heat is evolved out. That means basically here higher energy before the reaction, here is a higher temperature, higher energy. Okay, so when the reaction is exothermic, so first of all the direction of reaction is A converts into B, means product side. So same as there is a loss of energy, means energy is rises, and when energy is rises, so that time the equilibrium is shifted towards the left side because of it is a lower temperature condition, because product side has higher temperature condition, that means here is a lower temperature condition, and when temperature is increases, K is increases, K is a equilibrium constant, and it always influence to the direction of the formation of product. So K is very important. At higher temperature, K is increases. If temperature is decreases, K again increases. Means in exothermic reaction and endothermic reaction, always when we change the temperature, the product is always formed as a higher yield. As a higher yield product will be formed. And for endothermic reaction, there is a delta H is negative. Delta H is negative means suppose A to B is there. A to B is there. So what happened here in endothermic reaction, the energy is added. So the energy is added at which side? Reactant side. So plus delta H is here, which is added because endothermic reaction means absorb the energy, absorb the temperature. So that time here temperature is will increases. So when temperature is increases, it shifted towards the lower temperature side. When it shifted to the low temperature side, again A converts into B because it is a lower temperature side. So here at lower temperature, K also increases, means equilibrium constant increases, rate of reaction increases. So at lower temperature, K also increases, at higher temperature, K also increases, means when at equilibrium condition temperature is changes, increases or decreases, it always favors to the formation of the product. So this is a two important conditions we consider here, because we already in last lecture we discussed the effect of concentration. So next point we are going to discuss here the want of equation. Okay, so we discuss here want of equation. Okay, so the point is want of equation. So basically it is considered which is based on the relationship between the standard Gibbs free energy and equilibrium constant for the gaseous reaction. Kp is the equilibrium constant for the gaseous reaction. We already know this relationship between the delta naught G and Kp we already discussed, and the equation is delta G naught is equal to minus RT ln Kp. We assume this equation in relationship between the standard Gibbs free energy and equilibrium constant of the pressure condition, means gaseous reaction. So if we consider this equation here, using this equation we can find out the value of ln Kp. So ln Kp is equal to, so if is here this minus RT comes to this side, so ln Kp is equal to the minus sign for here, so minus delta naught G upon RT. We rearrange this equation here, but we already know what is the standard Gibbs free energy. So delta G naught is equal to delta H naught, means standard enthalpy minus standard entropy T delta naught. Yes, we already have this equation. because here you know G is equal to H minus T delta S. Okay, or delta G is equal to this one. So this is the change in free energy. So here standard free energy is equal to, just here we add the node, means it is a standard condition. So we already have this, we get this equation after the rearranging the relationship between the standard gives free energy and Kp. So this is the equation which is required. We rearrange here, but we have this value, so we put the value of delta G is here. So ln Kp is equal to, so what is the value of delta G? It is the delta H naught upon RT minus delta S upon R, because here if we consider same, here we place RT is here, means how this come? If we add this way, delta S naught T delta S naught upon RT, TT is cancelled, that means just what remain here, delta S naught upon RT. Okay, so once we get this, so we have the equation number 1. This is the equation number 1. So delta H naught and delta S naught are the temperature independent. So equation 1 we return between the two temperature conditions, T1 and T2. If there is a T1 and T2, so for ln Kp, again there are two conditions are established, P1 and P2. So two different temperature conditions having the two pressure conditions. So this equation written as the same, but just we return between the two temperature. That means for one, ln Kp1, P1 condition, so here is a T1. Second one, Kp2, here is a T2 is condition, other conditions remain same. So at T1 condition we get this equation number 2, at T2 condition we get the equation number 3. Just Kp1, Kp2, T1 and T2, we just write this equation number 1 between the two temperatures. So we get the another two equations, equation number 2 and equation number 3. So here we subtract the equation number 2 from equation number 3. So we subtract this from equation number 2, that means it considered as a T2 is a higher temperature, so higher temperature condition is means lower temperature condition is subtracted from the higher temperature condition. So here ln Kp2 minus ln Kp1, so this side is the subtraction, and this side here delta H naught upon R. So here delta H naught, here is delta H naught upon R. These are the same value. These are the same value because they are temperature independent. So what remains? So delta H naught upon R remains same. It is considered as a constant. There is a temperature independent. This also temperature independent. So what remaining? There is a T1. So 1 upon T1 and 1 upon T2 is considered. So there is a equation number, subtract the equation 2 from 3, means T2 minus T1 is here. So it is 1 upon T2 minus 1 upon T1. So entropy is neglected, it is a temperature independent, there is no need of entropy in an equation. So enthalpy is the energy state, enthalpy is the heat content of the system, that means it required but it is remains constant. So we write this equation as ln Kp2 minus ln Kp1 is equal to delta H naught, this minus sign as a positive, so here there is no negative sign, and here what remains, here is a T1 upon T1 minus T2 is to be considered. So here the reaction condition, this is the equation number 4, which consider it is a one of the form of Van't equation. One of the form of Van't equation. Suppose we know the one of the equilibrium constant value at one temperature, we can find out the equilibrium constant value at another temperature. So one of the condition we know it, we can find out the later condition or second condition. What happened means how equilibrium constant is changed in second condition. So for that, Van't equation is very important to calculate, to find out the equilibrium constant at another condition. So we are going to solve the problem which is based on Van't equation. Okay, so first problem is given to you. The equilibrium constant for the synthesis of ammonia it is the reaction is 6.2 into 10 raised to 5 at 298 Kelvin. Predict the value at 400 Kelvin, and the heat of standard heat of formation of NH3 is given is 46.11 kilojoule per mole. So first to know, to understand the what is given and what asked to be find it. Okay, so the reaction is given, it is a synthesis of ammonia. Okay, and for that the equilibrium constant is given, and at what temperature? 298 temperature, means at T1 the equilibrium constant is given. And what asked to find out the equilibrium constant at T2 means at 400 Kelvin. So for that the heat of formation is given. So if we use Van 't Hoff equation, we must have the value of heat of reaction, and heat of reaction is the sum of heat of product minus sum of heat of reactant, heat of formation of reactant, product minus heat of formation of reactant. So here first of all we find out heat of reaction. So here what is the reaction? It is the given. So here 2 into heat of formation of NH3 minus 1 into heat of formation of N2 plus 3 into heat of formation of H2. Okay, so put all values here. So 2 into what is the heat of formation of NH3, which is given here, minus 46.11. Okay, minus here 1 into, is it heat of formation of N2 is given? No. So 1 into 0 plus 3 into, is it heat of formation of H2 is given? No. So again here is the 0. That means here is a 0 0. So we just directly write here, it is the minus 92.11 kilojoule per mole, because the values are not given here. So okay, we find out delta H naught, standard heat of formation. So we use the Van 't Hoff equation. So what is the Van 't Hoff equation? It is the ln Kp2 minus ln Kp1 is equal to delta H naught upon R, here 1 upon T2 minus 1 upon T1. This is the first equation. So we write this equation as a, so it is a ln Kp1 upon ln, this is the ratio which is considered, ln Kp1 upon ln Kp2 is equal to delta H naught upon R, and then 1 upon T2 minus 1 upon T1. So we put all values here first of all. So it is the ln Kp1. This is the first value which is given to you, and the value is given is the equilibrium constant is given. This is at T1 condition, so it is the equilibrium constant. So ln, put the values here, 6.2 into 10 raised to 5, and here Kp2 we are going to find it. Then we already have the value of delta H naught, we already find is here. So minus 92.11 upon R. So what is the value of R? So value of R here is considered, it is a 0.00831. It is the 0.00831, which is considered the universal gas constant value. Okay, yes, it is a 831. Then into 1 upon, what is the value of T2? It is given to you 400. Okay, minus what is the value of T1? It is a 298. So we put all the values here. Then so we solve it first. When we solve it first, ln 6.2 into 10 raised to 5 upon Kp2 is equal to, when we solve it, the value is 9.49. You solve it, solve this one, this one, this one, and finally we get the answer is 9.49. So it is 9.49. So ln Kp2 is equal to ln Kp2 is equal to this ln is goes here, so ln 6.2 into 10 raised to 5 minus 9.49 and the ln Kp2 is equal to, the answer is, just a minute, the value which is given here minus 5 sign is given here, so you just make a changes here, minus 5 10 raised to minus 5, okay, 10 raised to minus 5 10 raised to minus 5. So when we solve it, the answer is 3.92, sorry, 93.88. okay, so Kp2 is equal to 51.41. So you can solve the numerical problem using the calculator. Without calculator, don't try to solve it. Do all the calculation one by one in calculator and then solve the values. So you may increase the steps here. You solve one by one. Okay. Then take this value comes up to this value and then solve the other. So the equilibrium constant at second equilibrium constant is given, it is a 51.41. So once we have the value of one of the equilibrium constant, one of the condition, we can find out the second condition and second value using the one-top equation. So this is the application of one-top equation. Same as the second problem is given to you. Okay, so similarly you can solve second problem which is given to you. It is solve problem. So today we stop here. So we will discuss some other concept in next lecture.